Consider a single electron. Fire it down a tube toward a barrier cut with two narrow slits and let it land on a screen on the far side. Fire it completely alone, with nothing else near it, no other particle anywhere in the machine. Do this one electron at a time, thousands of times over, and something impossible slowly appears. The dots stack up into a striped pattern of bright bands and dark gaps, the exact signature of a wave that went through both slits at once and interfered with itself. Physicists first pulled this off with genuine single electrons in 1974. Not a beam, not a crowd. One particle in flight at a time, with long, quiet gaps between each launch. Each electron strikes the screen as a single point, in one definite spot the way a thrown pebble hits a wall, and yet the pattern those points build, band for band, is the striped pattern of a wave. It matches the wave result perfectly, as if the whole experiment had been run with ocean swell instead of tiny bullets. That is the strangeness we are settling into here. A thing that arrives as one dot behaves, on the way there, as if it explored every path it could have taken. Before we go deeper, one small thing. If you find this quietly fascinating, a like or a subscribe genuinely helps this channel keep making these. We're on Spotify too, if you drift better with just the voice. That is the whole ask. Now let the strangeness back in. Start with what almost everyone pictures. You imagine a particle as a tiny ball, a hard little speck that is always somewhere, at every instant whether or not you are watching. It has a position, it has a path. If it went through a barrier with two slits, it obviously went through one of them, the left or the right, and you simply did not happen to see which. That is the common sense story, and it is the story your whole life has trained you to expect. Quantum mechanics says that story is wrong. Not slightly wrong, wrong at the root. The truth. The equations describe is stranger and quieter. Before you measure it, a particle does not carry one position tucked away somewhere. It carries a spread of possibilities all at once, blended together, each possible outcome weighted by a number. That blend has a name. It is called a superposition. And the mathematics that holds it, that carries the whole spread of possible answers from moment to moment, is called the wave function. The wave function is the closest thing physics has to a portrait of a particle between measurements. It is not a picture of a ball at a location. It is a shape spread across space, tall in some places, low in others, and it tells you how the possibilities are distributed. When the wave function is tall somewhere, that spot matters. When it is flat, that spot barely counts. And crucially, the wave function can pass through both slits at the same time and overlap with itself on the far side, high crests meeting high crests, crests meeting troughs and cancelling out. That overlap is the interference. That is why the bands appear. So think of the screen not as a wall being hit by bullets, but as a still pond seen from above. Drop two stones close together, and the ripples spread out in overlapping rings. Where crest meets crest, the water heaves high. Where crest meets trough, the water goes flat and still. Freeze that pattern of high and calm water, and you have rings of activity and rings of nothing, exactly like the bright bands and dark gaps on the electron screen. Now here is the part that refuses to sit still in your head. With the electrons, only one stone was ever dropped at a time. The ripples that interfered with a single particle overlapping with its own possibilities. For a long time this looked like a story only about light. Thomas Young ran the two-slit experiment with a beam of light in 1803, more than a century before anyone spoke of quantum anything. He saw the same banded stripes and concluded correctly for his era that light must be a wave. That settled a long argument. Light was a wave, the way sound is a wave, the way water is a wave. Matter was something else. Matter was made of little solid pieces. The two worlds seemed clean and separate. Then, a French graduate student blurred the line on purpose. In his 1924 doctoral thesis in Paris, Louis de Broglie asked a question that sounds almost reckless. If light long thought a pure wave, could also behave like a stream of particles, then why should matter not run the other way? Why should an electron, long thought a pure particle, not also carry a wave? He wrote down a short relationship for it. The wavelength of any object equals a tiny fixed number, Planck's constant, divided by the object's momentum. In symbols, lambda equals h over p, small constant on top, the object's mass and speed on the bottom. That little formula quietly explains why you never see any of this in ordinary life. Run the numbers on a thrown baseball. Its momentum is enormous compared to that tiny constant, so its wavelength comes out to roughly 10 to the minus 34 of a meter. That is a decimal point followed by 33 zeros and then a 1 in meters. It is unimaginably smaller than the nucleus of a single atom. A baseball does have a wavelength in principle. It is just so absurdly tiny that nothing in the universe could ever detect its waviness. The ball is, for all practical purposes, only a ball. Now run the same numbers for an electron. An electron is fantastically light, so its momentum is tiny, so its wavelength swells up to something comparable to the spacing between atoms in a crystal. That is the whole difference. That is why the wave hides in a baseball and shouts in an electron. The electron's wave is big enough, relative to the world around it, to visibly bend and spread and interfere. De Broglie's idea was bold enough that many physicists doubted it. Albert Einstein did not. Einstein read the thesis and endorsed it, which carried real weight, and the doubt began to soften. Then came the proof. In 1927, two researchers in the United States, Clinton Davison and Lester Germer, fired electrons at a crystal of nickel and watched the electrons scatter off the orderly rows of atoms. The pattern that came back was a diffraction pattern, the fingerprint of waves bending around a regular grid. Electrons, solid particles with mass and charge, were behaving as waves. The line between matter and wave had officially dissolved. So an electron is a wave. But a wave of what? Not a wave in water, not a wave in air. When one electron finally lands, it does not smear itself gently across the screen like a spreading ripple. It makes a single sharp dot in one place. So whatever is waving, it is not the stuff of the electron itself sloshing around. The answer came in July 1926 from Max Born, and it is one of the deepest ideas in all of physics. Born proposed that the wave function is not a wave of substance at all. It is a wave of probability. The height of the wave at any point does not tell you how much electron is sitting there. It tells you the odds of finding the whole electron there if you look. More precisely, you take the wave's amplitude at that point and square it, and that squared value gives you the probability of a hit right there. Sit with what that means. Where the wave is tall, the squared amplitude is large, and the electron is likely to land. Where the wave is low or cancelled to nothing, the probability is near zero, and the electron almost never lands. The bright bands on the screen are simply where the two overlapping waves reinforced, so the odds ran high. The dark gaps are where the waves cancelled, so the odds fell to nothing. The interference pattern is a map of probability, painted one certain dot at a time until the shape of the odds becomes visible. Born won the Nobel Prize in 1954, largely for exactly this insight. This is what people mean, at bottom, when they say a particle is in superposition. It is not sitting in two places in the ordinary sense, one copy here and one copy there. The wave function, each with its own share of the odds set by Born's rule, until a measurement reaches in and pulls out exactly one. If probability feels too abstract to hold, try the coin. Flip a coin high into the air and watch it spin. While it spins, blurred, you're tempted to say it is secretly already heads or tails, and you just cannot read it yet. For an ordinary coin, that is true. But a quantum coin, spinning, is not secretly one face waiting to be caught. It is genuinely both faces at once, blended into a single blurred state, and it stays that way until it slaps flat onto the table and is forced to show a single side. The flattening is the measurement. The spin is the superposition. There is no hidden answer during the spin. There is only the blur and the odds. Hold both pictures together now, because together they carry almost the whole mystery. The overlapping ripples frozen on the screen give you the wave, spread across both paths, interfering with itself. The spinning coin, genuinely both faces midair, gives you the blend, real and undecided, not merely unknown. That is what the wave function is doing between the moment you launch a particle and the moment you catch it. It is spread out, exploring, weighing every route, a cloud of maybes rather than a fact. And here is where the experiment turns genuinely eerie, where the calm mathematics starts to feel like it is watching you back. Go back to the two slits and the single electrons building their beautiful striped pattern, dot by patient dot. Now, change one thing, place a small detector at the slits, a device whose only job is to note which slit each electron actually passes through, left or right. Nothing else about the setup changes. Same electron, same launcher, same screen. The stripes vanish. The moment you can tell which slit each electron took, the interference pattern collapses. The dots stop building bright bands and dark gaps. Instead, they pile into two plain clumps, one behind each slit, exactly the way ordinary bullets would stack up if you fired them through two holes in a wall. The wave behavior is simply gone. The particle stops exploring both paths and starts committing to one. Turn the detector off, and the stripes quietly return. Turn it back on, and they die again. Read that carefully, because it is easy to smuggle in a comforting explanation that is wrong. The tempting story is that a human being peaked, and the electron somehow got shy. That is not what the equations say, and it is not what the experiments show. What matters is not a pair of eyes. What matters is whether the which path information exists anywhere at all, whether the fact of left or right has been recorded somewhere in the world. Nobody needs to read the detector. Nobody needs to know. The instant the path becomes knowable, the instant that information is written into the machine, the interference is destroyed. So the universe is not reacting to your attention. It is reacting to information, to knowability itself. The presence of a which path record sitting there unread is enough to force the particle to behave like a single bullet on a single path. That is a very strange thing to be true, and it is one of the most reliably confirmed facts in all of physics. Niels Bohr had a name for this two-faced behavior. He called it complementarity, and he laid it out formally in September 1927. His claim was that the wave description and the particle description are both completely true and both completely necessary, but they can never be seen at the same time. Which face reality shows you depends entirely on the question you decide to ask. Ask which slit. Set up the machine to answer that, and you get particles, two tidy clumps. Ask about interference instead. Leave the path unknown, and you get waves, the full striped pattern. You choose the question. Reality answers, honestly, in the language your question demanded. But you can never make it answer both at once. This is the point where most people quietly want to ask the obvious thing. Which is it really? Between the launcher and the screen, in that dark stretch of travel, was the electron truly spread across both slits like a wave, or did it secretly go through one and we simply lack the tools to see? A century of the sharpest minds alive have circled that question and failed to settle it. Some say the spread is real, that the particle genuinely tries all paths. Some say the wave function only measures our ignorance, that a single hidden truth is waiting underneath. By the end of tonight you will understand why that argument has never been won and why it may be the deepest open question in science. For now, stay with the plain, astonishing facts, because the facts alone are enough to keep you awake if you let them. A single particle, fired utterly alone with nothing in the universe to interfere with, still manages to interfere with itself. For a few billionths of a second it behaves as if it tried both routes through space at the same time, weighing each one, before it finally commits to a single dot on a screen. The wave function carried every possibility. The measurement kept only one, and which one you get is never certain, only likely, set by the square of a wave of pure probability. You feel none of this in your own life for one simple reason. Your wavelength, like the baseballs, is so vanishingly small that your waviness could never show. You're always, as far as you can ever tell, in one place, on one path, a single, solid fact. But that solidity is a feature of your enormous size, not a law of the deep world. Shrink down to the electron, and the single facts dissolve back into clouds of maybe. To understand how anyone came to believe that a particle could behave this way, you have to go back long before anyone spoke of quanta at all. The first clue was hiding in plain light. In 1803, an English physician named Thomas Young cut 2 narrow slits in a screen and let a single beam of sunlight fall through them. On the wall behind, he did not find 2 bright lines. He found a whole row of them, bright band, dark gap, bright band, marching evenly across the surface. Those bands could only mean one thing. Light was arriving in crests and troughs, overlapping, adding where they matched and cancelling where they did not. Light was a wave, and Young had the striped shadow to prove it. That was more than 100 years before quantum mechanics had a name. For a long time the lesson seemed to belong only to light. Waves were waves, and matter was matter, and the two did not trade places. A stone was a stone. An electron, once it was discovered, was pictured as a tiny hard speck, a grain of electricity, nothing at all like a ripple on a pond. Nobody expected the striped shadow of Young's experiment to have anything to say about solid things. Then came a quiet young French aristocrat with an unreasonable idea. His name was Louis de Broglie. In 1924, at the Sorbonne in Paris, he wrote a doctoral thesis so strange that his own examiners were not sure what to do with it. He asked a simple question that no one had dared to take seriously. If light, long thought to be a wave, could also behave like a stream of particles, then why should the reverse not be true? Why should matter, long thought to be particles, not also carry a wave? He wrote down a single short equation to say exactly how long that wave would be. The wavelength, he claimed, equals Planck's constant divided by the momentum. Lambda equals h over p. The faster and heavier a thing moves, the shorter its wave, until the wave shrinks to nothing you could ever hope to see. That last part is why the idea sounds harmless for everyday objects. Run the numbers on a thrown baseball, and the wave that rides along with it is about 1/trillionth of the width of an atom's core. It is there in principle and utterly invisible. But run the same numbers on an electron and something changes. Its wave comes out roughly the size of the spacing between atoms in a solid crystal. Small, yes, but no longer beyond reach. For an electron, the waviness is not a rounding error. It is large enough, in the right setting, to leave a mark. At first, almost nobody believed him. A wavelength for matter sounded like poetry dressed as physics, a neat symmetry with no evidence behind it. The thesis might have quietly vanished into a drawer. It was rescued by the most famous physicist alive. When Albert Einstein read de Broglie's work, he did not laugh. He wrote to a colleague that the young Frenchman had lifted a corner of the great veil. That single endorsement changed everything. Suddenly the idea carried Einstein's weight, and experimenters who trusted Einstein began to wonder whether matter waves could actually be caught. The proof, when it came, arrived partly by accident. In the United States, 2 researchers named Clinton Davison and Lester Germer were firing electrons at a target of nickel and watching how they bounced back. It was patient, unglamorous work, and for a while it showed nothing unusual. Then a piece of laboratory glass shattered. Air rushed into their apparatus and spoiled the nickel surface with a film of oxide. To repair it, they heated the metal strongly to clean it off. That heating did something they had not planned. It reshaped the nickel. Where the surface had once been a jumble of tiny crystals, it now settled into a few large, orderly ones, with their atoms lined up in neat repeating rows. When they went back to firing electrons at this newly ordered surface, the results were no longer plain. The electrons came off at particular angles, bunched into strong beams in some directions and almost none in others. This was not how little hard specks were supposed to behave. It was, however, exactly how waves behave when they scatter off a regular grid. The rows of nickel atoms had acted like the slits in Young's old experiment, only far finer, spaced to match the tiny wavelength de Broglie had predicted. The electrons had ridden in as waves and rippled back off that nickel mirror the way light dances off the surface of moving water, spreading into crests and hollows you could actually measure. That was 1927, and the case was, in one sense, closed. Matter was wavy. Not as a metaphor, not as a trick of light, but as a measured fact about electrons scattering off metal. De Broglie's short equation held. Within a few years he would receive the Nobel Prize, and the accidental broken glass in Davison's lab would be remembered as one of the luckier mishaps in the history of science. You can measure the wavelength of a thing you once called solid. That sentence would have sounded like nonsense a single generation earlier, but proving that matter is wavy did not settle the deeper unease, it sharpened it. Because now there were two pictures of the same electron, and both of them were backed by hard evidence. Point a detector one way, and the electron behaves like a particle, a single countable arrival, one click, one dot. Set the experiment up differently and the very same electron behaves like a wave, spreading, overlapping, interfering with its own possibilities. Which one is the electron, really? The honest answer, in 1927, was that the question itself might be broken. The man who said so most clearly was the Danish physicist Niels Bohr. That same September, he stood before an audience in Italy and offered a way of thinking that he called complementarity. His claim was careful and strange. The wave description and the particle description are both true. Neither is a lie, and neither is the whole story, but they can never be seen at the same time, in the same experiment. They are like two faces of one object that can only ever be turned toward you one at a time. Ask a wave question, and nature answers with a wave. Ask a particle question, and nature answers with a particle. What you cannot do is force it to answer both at once. Sit with how radical that is. Bohr was not saying the electron is secretly a wave that only looks like a particle, or secretly a particle that only looks like a wave. He was saying the description you get depends on the choice you make about how to look. The measurement is not a neutral window onto a fact that was already sitting there. The measurement is part of what fixes the answer. Change your question, and you change which side of reality turns to face you. That was the uncomfortable settlement the founders reached. Young had shown that light interferes. De Broglie had dared to say that matter must interfere too. Einstein had lent the idea his name. Davison and Germer had caught electrons rippling off nickel and turned the guess into a measurement, and Bohr had drawn the moral that a single thing can be wave and particle both, depending entirely on the way you choose to catch it. A century of physics was built on that foundation, and it worked. The equations predicted everything, right down to the fine detail. Yet notice what all of it circles around and never quite touches. Every one of these discoveries leans on the same quiet hinge. The wave spreads out, exploring, trying its possibilities, as long as no one pins it down. The moment you insist on a definite answer, the wave gives way to a single dot on a screen, a single click in a detector, a single face turned toward you. The spreading and the pinning down are two different behaviors, and the switch between them happens exactly when a measurement is made. Complementarity described that switch beautifully. It did not explain it. Bohr told you which face you would see. He did not tell you what happens, physically, in the instant the choice is made. So the detective story that began with striped shadows on a wall ends here, with a puzzle rather than a period. Matter is wavy. That much is settled, measured, and beyond doubt. Each particle behaves, when left alone, as if it is quietly sampling every path open to it. But if a single particle can quietly try both paths at once, one question refuses to go away. What happens the moment something finally looks? But if a single particle can quietly try both paths at once, one question refuses to go away. What happens the moment something finally looks? Here is the problem in its bluntest form. The Schrödinger equation, the master equation of the whole theory, describes quantum states evolving smoothly. It is deterministic. It is reversible. Feed it a particle spread across two paths, and it hands you back a blend, a superposition, growing and shifting like a slow tide. Nothing in that equation ever picks. Nothing in it ever snaps to one answer. And yet every real measurement, in every real lab, on every day this experiment has ever been run, gives you exactly one definite result. One dot on the screen, one reading on the dial, one outcome, sharp and single. That gap has a name. Physicists call it the measurement problem. The smooth equation says blend. The world hands you a single fact, and the standard mathematics has no built-in step that explains the jump from one to the other. There is no line in the theory that says, here, at this moment, the blur becomes a choice. It simply must, because it always does, and nobody wrote down why. Before we go further, one small thing. If this quiet unravelling of certainty is the kind of strangeness you like to fall asleep to, a like or a subscribe helps this channel keep making it. And these scripts live on Spotify too. That is the whole ask. Now let the door of the lab swing shut and follow the thing inside. The most famous version of this puzzle is a cat. In November of 1935, Erwin Schrödinger published a long paper with a heavy German title, Die gegenwärtige Situation in der Quantenmechanik, which means the present situation in quantum mechanics. Buried inside it was a thought experiment he never expected to become a legend. He was not proposing it as a wonder. He was proposing it as a complaint. Picture the setup exactly as he built it. A steel box, sealed and silent, sitting on a bench. Inside the box, a single radioactive atom. Beside the atom, a Geiger counter, waiting to hear it decay. Wired to the counter, a hammer. Under the hammer, a glass vial of poison gas. And in the box, breathing, a cat. If the atom decays, the counter clicks, the hammer falls, the vial breaks, and the cat dies. If the atom does not decay, nothing happens, and the cat lives on. Now here is where the ordinary logic breaks. The atom is a quantum object. Until it is measured, the mathematics says it sits in a superposition of decayed and not decayed, both at once, in the same weighted blend we met at the slits. But the atom is chained, step by step, to the hammer, to the vial, to the animal. So if you take the equation literally and follow the blend outward, the cat is dragged into the same state. Alive and dead, superimposed, until the lid comes off. That was Schrödinger's point, and his joke. He did not believe in a smeared cat. He built the box precisely to show how absurd the theory sounds when you scale it up from a single atom to a warm, living thing. He was mocking the reigning view, the one taught out of Copenhagen, that a quantum system has no definite value until it is observed. Fine for an electron, he was saying, but run the same logic up the chain, and it asks you to believe in a creature that is genuinely neither living nor dead, waiting on a photon. Picture that sealed steel box for a moment, holding what the mathematics insists is a blended ghost state, not a hidden either-or, but a real superposition of alive and dead, folded together, resolving into one or the other only when light finally reaches inside. It is an image built to feel ridiculous. That was the design. And the strangeness is that a century later, nobody can say cleanly where the ridiculousness ends and the physics begins. Schrödinger was not writing in a vacuum. His cat was part of an argument, and the other side of that argument was Einstein. Earlier that same year, in 1935, Einstein had published a paper with Boris Podolsky and Nathan Rosen, now known everywhere by their three initials, EPR. Their claim was sharp. Quantum mechanics, they argued, must be incomplete. It implied that two particles could be linked across any distance. so that measuring one instantly fixed the other, with nothing travelling between them. Einstein could not stomach it. He called it spooky action at a distance. To him, that spookiness was not a discovery. It was a symptom, a sign the theory was missing something underneath. Schrödinger read the EPR paper, and it lit something in him. His cat was his own contribution to the same unease, aimed at the same soft spot. If you take this theory at its word, he was saying, look what you are forced to swallow. A poisoned cat in a box, neither one thing nor the other, until you choose to check. Two of the century's greatest minds circling the same doubt and neither able to close it. The trouble is that the doubt was not new, and it had already been written into the machinery of the theory itself. 3 years earlier, in 1932, the mathematician John von Neumann had laid out quantum mechanics with a rigour no one had matched, and in doing so he made the split explicit. He described the theory as running in two separate modes. In the first mode, the state evolves smoothly and deterministically, following the Schrödinger equation, blending and spreading like the tide. In the second mode, the instant a measurement happens, the state suddenly, randomly collapses to a single outcome. Two rules, stitched together, one continuous, one abrupt, one with no chance in it at all, one built entirely out of chance. Neumann wrote both down side by side, and the theory has carried them ever since. But he could not say what physically triggers the switch from the first to the second. Nobody could. It was a patch, an honest one, laid over a hole no one knew how to fill. When does the smooth become the sudden? What counts as a measurement exactly? The mathematics simply names the moment and moves on. You can feel how uncomfortable that is. Every other equation in physics tells you how something changes over time, step by continuous step. Here the theory has a second rule that reaches in from outside the equation and says, now stop being a blend, now be a fact. And it never explains itself. If the cat made the problem vivid, a later thought experiment made it worse. It came from Eugene Wigner, and it is usually called Wigner's friend. Take the sealed lab and put a person inside it. A friend, a competent physicist, who measures a quantum particle and gets a clear, definite result. From that friend's point of view, inside the room the measurement is over. The particle chose. The fact exists. But now stand outside the sealed door where Wigner stands. From out here you have not interacted with anything inside, so by the same mathematics, the same theory the friend used, you must describe the entire lab, the particle, and the friend together as one giant unmeasured superposition. Your friend, in your description, is in a blend of having seen one result and having seen the other. The event has not happened yet, as far as your equations are concerned. Picture the two of them. Two physicists standing on opposite sides of a single lab door. The one inside says the experiment is finished, the answer is in, it is done. The one outside, using equally valid quantum mechanics, says the whole room is still an unresolved blur, the friend included, nothing settled. And here is the part that should stop you cold. By the mathematics, both of them are right. There is no line in the theory that overrules one in favour of the other. Two valid observers, in genuine disagreement about whether an event has even occurred. That is not a loophole someone forgot to close. It is a live wound in the theory, and it keeps bleeding new work. Recent extensions of Wigner's friend have made it sharper still, turned it into formal no-go theorems, proofs that certain comfortable assumptions cannot all be true at once. This is not idle philosophy at the edges. The problem is serious enough that modern versions of it have won major prizes in the field for the researchers who push them furthest. Nearly 60 years after Wigner first posed the puzzle, it is still generating results, still unresolved. And if you want proof that the experts have not quietly agreed on an answer, consider how they describe themselves. A survey of the field's own literature taken in 2024 offered a wry summary. There are, it said, 3 types of quantum physicists. There are those who think quantum mechanics is defaced by a measurement problem, a genuine flaw at its heart. There are those who think there is no measurement problem at all, that the discomfort is a confusion we should have outgrown. And there are those who think the whole question is simply not worth serious thought, and would rather get on with the calculating. Sit with that for a second. This is one of the most successful theories ever built. It predicts the behavior of atoms and light to a precision that borders on the absurd. It runs the transistors under your fingers, and the people who use it every day cannot agree on whether its central mystery is a crisis, a non-problem, or a waste of breath. That is not the picture of settled science. That is a 100-year-old argument that has never been won. What makes the cat so hard to wave away is that nothing in the equations draws a line for you. There is no clause that says an atom may be blended but a cat may not. No clause that marks a friend or a boulder or a galaxy as too large to be described this way. The mathematics is scale invariant. It applies the same rule to a single electron and to the animal in the box, and it never once tells you where to stop. Only convention stops you. Only intuition, and the plain fact that you have never seen a smeared cat draws the boundary. The theory itself is silent. Schrödinger built his box to prove the theory absurd if taken literally. He assumed everyone would agree the cat was a step too far, that the blend must break somewhere before it reached a living thing. And nearly a century on, the joke has curdled into a genuine open question. Physicists still cannot agree on the point at which the superposition stops being absurd and starts being how reality actually works. Some say the line is real and physical. Some say it is only practical, a matter of how fast the blur leaks away. Some say there is no line at all, and the cat really is smeared for the barest instant before the world catches up. That last idea is the one worth holding on to as we go on. Because notice what keeps happening in every version of this puzzle. The atom stays blended while it's alone and undisturbed. The cat only seems to resolve when the lid comes off and light floods in. The friend's result only seems settled once it has leaked past the sealed door. In every case, the blur survives in isolation, and the definite outcome appears the moment the system touches something larger than itself. The counter, the air, the light, the rest of the room. Maybe the observer was never the point. Maybe consciousness, the human peering in, was always a distraction dressed up as an explanation. What the cat and the friend really share is a chain of contact reaching outward, atom to counter to hammer to air to eye, each link tangling the quiet blend with more and more of the world. And somewhere along that chain, reliably, silently, the blend stops being a blend. So the real question sharpens into something almost embarrassingly simple. Why does the blur vanish the instant the wider world gets involved? So the real question sharpens into something almost embarrassingly simple. Why does the blur vanish the instant the wider world gets involved? The answer physicists reach for is a single long word, decoherence, and it is less a dramatic event than a slow leak. A superposition is not destroyed by a hammer blow. It drains away. It bleeds out into everything around it, one tiny contact at a time, until nothing coherent is left to see. Think about what surrounds any object right now. Air molecules by the trillion, striking it billions of times each second. Stray photons of light and warmth, landing and bouncing away. Faint thermal vibrations shivering through every solid surface it touches. To your eyes, none of that matters, but to a quantum state, each of those contacts is a question. Each collision asks the object where it is, and the object answers, and that answer escapes into the environment. That is the whole mechanism, and it is worth slowing down over. When a particle is in superposition, its two possibilities are held together in a delicate kind of agreement, a matched rhythm that lets them interfere. Decoherence is simply that rhythm getting recorded, over and over, by the outside world. An air molecule bounces off the left possibility differently than the right one. Now the molecule carries a trace of which was which, then a photon does the same, then another and another. Before you go on, if this is loosening the knots in your head a little, a quiet like or subscribe genuinely helps this channel keep going, and every episode is on Spotify too. That is the only thing I will ask of you tonight. None of those single traces amounts to much. No air molecule knows anything. But the information is now out there, smeared across 1,000 tiny messengers, and it can never be gathered back. That is the key. The which path information does not need a scientist to read it. It does not need eyes, or a mind, or an instrument. It only needs to be recorded somewhere in a way that cannot be undone. Once that happens, the interference is gone. The two possibilities can no longer overlap and cancel and reinforce, because the universe now, in some faint sense, already knows them apart. Here is a way to feel the difference. Picture a coin spinning cleanly on a table in an empty, silent room. It spins and spins, a bright blur that is neither heads nor tails. Now picture the same coin, but jostled by a dozen unseen hands every microsecond, tapped and nudged from every side without a moment's rest. It cannot hold that spin. It clatters flat almost at once. The empty room is a single, isolated atom. The jostled coin is a book on your desk, a cup your own hand. Everyday objects are jostled constantly, which is exactly why you never catch them mid-blur. That word, jostled, is the honest picture of your whole world. Nothing large is ever left alone. A dust mote in a sunbeam is being battered by light and air so relentlessly that any superposition it might form is erased in a span of time too short to name. This is why the strangeness never reaches your scale. Not because big things obey different laws, because big things are impossible to isolate. The bigger an object is, the more the world touches it, and the faster its coherence pours away into the noise. Now here is the part that matters most, and the part that gets skipped in almost every casual telling. Decoherence explains the disappearance of the blur. It does not explain the appearance of a single answer. Hold those two things apart because the difference is the whole unsolved heart of this subject. Decoherence tells you why you never see a live cat and a dead cat overlaid on the same lab bench. It tells you why interference patterns vanish the instant a detector records the path. It even tells you, with real mathematics, how fast that vanishing happens for an object of a given size at a given temperature. On all of that it delivers. It is one of the genuine triumphs of modern physics. But ask it the next question, the one a child would ask, and it goes quiet. Why is the cat you find when you open the box definitely alive rather than definitely dead? Why do you experience one outcome at all instead of the full smeared mixture the equations still contain? Decoherence turns a sharp superposition into a fuzzy list of possibilities and their odds. It never crosses out all but one line on that list. It never says, this one, this is what happened to you. The equations still hold every branch. Something about your single, definite experience remains unaccounted for. So decoherence does not close the case. It reshapes it. It takes the mystery of why the blur is invisible and dissolves it completely, and it leaves the deeper mystery of the single outcome standing exactly where it stood before. Keep that in your pocket for later. It is the thing the whole century of argument keeps returning to. For now, follow the practical side of all this, because it leads somewhere remarkable. If decoherence is the enemy, then keeping a superposition alive becomes a problem of isolation. You have to hush the environment, you have to stop the jostling, and the lengths engineers go to in order to do that are hard to believe until you see the numbers. Start with the air. Even a whisper of gas ruins everything, so the object is sealed inside ultra-high vacuum, a chamber emptied more thoroughly than the space between planets. Next comes motion itself, the tiny thermal jitter that every atom carries just from having a temperature. To quiet that, physicists use laser cooling, tuned beams of light that push against an atom's motion and slow it almost to a standstill. And then comes the cold, and the cold is the astonishing part. The processors at the heart of a quantum computer are chilled inside a dilution refrigerator, a machine that uses a mixture of two forms of helium to reach temperatures near the very bottom of what is physically possible. The target sits around 10 to 20 thousandths of a degree above absolute zero. Let that settle. The deep emptiness between the stars averages about 2.7 Kelvin. These machines run roughly 100 times colder than outer space. To keep a fragile superposition from leaking away, engineers build the coldest cubic inch in the known universe, and they build it on a bench, and they run it every day. If you saw one of these refrigerators, you would not picture a fridge at all. They hang like ornate golden chandeliers, tier below tier of gleaming plates, each stage colder than the one above it, hair-thin wires threading down through all of them to a single chip suspended at the frozen point at the bottom. Every layer is a wall against warmth. Every wall buys a little more silence, and in that silence a superposition can finally hold its breath long enough to be useful. How long is long enough? That question has become the headline number of the entire field. It is called coherence time, the span a quantum state survives before the environment erases it, and it is now tracked and published the way athletes track records. As of November 2025, a team at Princeton reported superconducting transmon qubits with coherence times crossing a full millisecond, reaching as high as 1.6 milliseconds. A millisecond sounds like nothing. It is the flap of an insect's wing, but scale it to the clock of the machine and it becomes an age. These processors tick at gigahertz speeds, billions of operations a second, so a single millisecond of coherence is millions of ticks of usable time. It is millions of chances to compute before the blur drains away and the answer decays into ordinary certainty. That Princeton figure was about 15 times longer than the qubits inside today's leading industrial machines, and roughly 3 times the previous laboratory record. In this field, tripling how long you can hold the bubble intact is an enormous stride. That is the tactile truth of it. Running a quantum computation is like holding a soap bubble intact through a hurricane, and every advance in coherence time is another few seconds you manage to keep the film from bursting. The whole art is not in building the bubble. Building it is easy. The art is in holding back the storm of the world long enough to use it, and now you tend to feel like a solid, single, sharply defined thing, sitting in one clear state, one clear place, moment to moment. But by the same physics, you're not exempt. You're made of the same particles that spread into blurs when left alone. The only reason you never feel any blur of your own is that you are the least isolated object imaginable. You're soaked in light. You're packed with warmth. You're entangled with trillions of air molecules and photons and surfaces every single nanosecond, each one recording where you are again and again faster than thought. Any quantum haze you might briefly carry is measured to death by your own environment instantly. It is erased before any instrument could catch it, and long before your own brain, itself a warm and noisy place, could ever register it. So you are not sharply defined because reality granted you an exception. You are sharply defined because you are watched so ceaselessly by everything that you are never given the chance to be anything else. The cold machines in their golden chandeliers are simply buying, for a millisecond, the solitude you can never have. They are engineering a scrap of the isolation the whole rest of the universe spends every instant destroying. That is the strange gift and the strange loss folded together. The blur is not rare because it is fragile in some special way. The blur is everywhere, constantly, in every particle you are built from. It just cannot last, because lasting requires silence, and the world is never silent. Decoherence is the sound of that world flooding in. The trick to catching the blur has a name that sounds almost gentle, a matter wave interferometer. The idea is older than any machine that runs it. If a single object truly moves as a wave, then that wave can be split. You can send one object down 2 paths at once, then fold those paths back together and watch what happens where they overlap. Everything depends on how you prepare the object first. You cannot toss a warm molecule into the machine and hope. It has to be made cold, and it has to be made slow. A fast, hot particle carries too much of its own restlessness, and its wave stays cramped and useless. So the object is chilled and gentled until its wave spreads out wide enough to work with. Then it drifts into the apparatus one object at a time. Inside, the wave is divided. In the Vienna Group's 2-meter interferometer, the machine that in 2019 sent a single molecule of nearly 2,000 atoms through as one quantum wave, the object's wave is coaxed across two separate routes through the same stretch of empty space. Neither route is the real one. Both are. The object is now smeared across a region far larger than the object itself. It has become, in the plainest sense, delocalized. Then, the two paths are brought back together. If nothing has disturbed the object, the two versions of its wave meet and interfere. Where the crests line up, the object is likely to land. Where crest meets trough, it is forbidden. Fire thousands of objects one after another, and they stack into a striped fringe. That fringe is the proof. A single object cannot make a fringe by taking one path. The stripes only appear if each object went both ways and met itself coming back. In January of 2026, the same Vienna team, Markus Arndt and Stefan Gerlich, with Sebastian Pedalino leading and Klaus Hornberger on the theory, pushed this further than anyone had. Their newer machine is called Muscle. Into it they sent nanoparticles built from clusters of 5,000 to 10,000 sodium atoms. Each cluster weighs about 170,000 atomic mass units, roughly the mass of a small protein, about 8 nanometers across. Too small to see, larger than any object caught this way before. Inside Muscle, each nanoparticle spread across a region dozens of times its own width. It held that spread for about 1/100th of a second, then landed and built the fringe. The team measured it as roughly 10 times more macroscopic than anything caught before. 1/100th of a second sounds like nothing. For an object of 10,000 atoms, it is astonishing it lasted at all. Here is why. Isolation is the entire game. The fringe is delicate beyond ordinary imagining. Anything at all that leaks out which path the object took will erase it, and the object does not need to be watched by a person. It only needs to leave a mark somewhere in the world. A single air molecule bouncing off it carries away that secret. A stray photon of heat, absorbed or emitted, does the same. The moment the environment records which way the object went, the two paths stop being versions of one object. They become two ordinary histories and the stripes dissolve into a plain smear. So the machine is built to give the environment nothing to record. The chamber is pumped down to a vacuum emptier than most of outer space, so almost no molecules are left to collide. The object is laser-cooled, so it is too cold to glow with its own heat. Every jostling molecule and every thermal photon that might carry the secret away is removed, one source at a time. What remains is a single object, alone, drifting through a darkness engineered to notice nothing. That is the closest thing physics has to threading a needle in the dark without letting the thread touch the sides. The thread is the object's own wave, split in two. The eye of the needle is the recombining point where the paths must meet, and the sides are the whole rest of the universe, every molecule and every photon waiting to brush against the thread and ruin the pass. Touch nothing, and the fringe survives. Touch anything, and it is gone. There is a second way to catch the blur, and it works from the opposite direction. Instead of sending an object flying and reading where it lands, you can hold the object still and question it in place. That is what a group at ETH Zurich did in May of 2023, and the object they used was large enough to see. It was a chip of sapphire, 16 micrograms, roughly 100 quadrillion atoms, several billion times heavier than a single molecule. A crystal you could rest between two fingertips. They chilled it near absolute zero and set its atoms vibrating. Then they placed it into a superposition of two opposite vibrations at once. The crystal was, in a real and measurable way, moving two ways at the same time. The distance between those two motions was tiny, about 2/1000th of a nanometer. But the object doing it was visible to the naked eye. You cannot read a state that small by looking. So the ETH team, Matteo Fadel and Marius Bild and their colleagues, borrowed a tool from quantum computing. They coupled the crystal's vibration to a superconducting qubit, a small loop of circuit that itself lives in a superposition of two states. The vibration and the circuit were wired together so that the crystal's quantum state could be written onto the qubit. The circuit became a translator. Whatever the crystal was doing, the qubit now carried a copy of it. Then they measured the qubit. A qubit is something you can read cleanly, the whole reason the machinery exists. And when they read it, the answer confirmed what the raw crystal could never show them directly. The sapphire had been vibrating two ways at once. They caught a visible object mid-superposition, not by watching it fly, but by teaching a circuit to speak for it. That same superconducting qubit holds the last piece of the picture, because it turns isolation into a currency. A qubit does not keep its superposition forever. It has a coherence time, a window in which the blur survives before the environment erases it. And a superconducting qubit runs fast. It clicks through operations at gigahertz speeds, billions of steps every second. Do the arithmetic and the stakes become clear. A coherence window of a single millisecond, 1,000th of a second, is millions of operations at that clock speed. In November of 2025, a Princeton group reported transmon qubits holding coherence past 1 millisecond, up to about 1.6, roughly 15 times longer than the qubits inside today's industrial machines. Every fraction of a millisecond you buy is more computation you can finish before the blur decays. This is why the whole enterprise runs inside dilution refrigerators chilled to 10 or 20 thousandths of a degree above absolute zero, about 100 times colder than the space between the stars. The cold is not for comfort. Every gain in isolation is bought and spent as time. So across both approaches, the flying nanoparticle and the held crystal, the same discipline holds. Prepare the object cold, split or excite its state, shield it from every whisper of the outside world, then read it fast before the world reads it first. In each case, what you recover is the same quiet fact. The object really was in two states at once, and the machine caught it in the act. And yet, for all that craft, notice what these experiments show and what they leave untouched. They prove the blur is real. They measure how long it lasts. They tell you exactly what erases it. Molecule by molecule, photon by photon. Every stripe on the screen and every reading off the qubit says the superposition was there, and every leak of isolation says why it fades. That fading is not a single dramatic snap. It is a slow bleeding of the secret out into everything nearby, and it has a name. Decoherence tells you why you never see the blur, but it never once tells you why the universe settles on this answer instead of that one. Decoherence tells you why you never see the blur, but it never once tells you why the universe settles on this answer instead of that one. It explains the vanishing, it does not explain the choosing. The interference leaks away into the air and the light and the warmth, and one outcome is left standing. But the equation stays silent about how that single outcome got picked. So the question does not disappear. It only changes hands. It passes from the engineers who cool the chips to the physicists who argue over what any of it means. Here is the part that should stop you cold. Put 4 of those physicists in one room. Show them the exact same sealed box, the one from before, with its atom and its counter and its quiet blended fate inside. Ask each of them one plain question. What just happened in there? You will get 4 answers, not 4 shadings of one answer. 4 different pictures of reality, flatly incompatible, and each one predicts the same experiment, down to the last decimal, every single time. If you take one thing from tonight, take that. And if this is the kind of question you like to fall asleep inside of, a like or a subscribe helps this channel keep making them. On YouTube or on Spotify, that is the whole ask. Now let the 4 of them talk. The first physicist is the oldest voice in the room. This is the Copenhagen view, shaped by Niels Bohr and Werner Heisenberg in the late 1920s. To this physicist, the wave function was never a real object floating in space. It was a ledger of your knowledge. It was a list of the odds. Before you open the box, the atom is a smooth blend of decayed and not decayed, and that blend is simply the most complete thing you're allowed to say. Then you measure. And in the measuring, the blend snaps to one value at random, with the odds set by the math. Ask this physicist how the snap works, by what physical gears, and you will get a shrug that has lasted 100 years. There is no mechanism, there is only the rule. The wave spreads, you look, reality commits, and the theory does not tell you why. The second physicist finds that shrug unbearable. This is Hugh Everett III, and the year is 1957, and the place is Princeton, where his doctoral thesis was supervised by John Wheeler and published in Reviews of Modern Physics. Everett looked at the collapse, that sudden random snap, and asked a simple thing. What if it never happens at all? What if the smooth equation is the whole story, all the way up with no special exception for the moment you look? Then the wave function does not collapse. It keeps evolving, and when the atom is both decayed and not, and the counter reads both, and you read both, the universe does not choose. It branches. It splits into two full copies of everything, one where the atom decayed and one where it did not, and each copy of you walks off certain that a single definite thing occurred. Picture that branching honestly if you can. Not one fork, once. Every quantum event everywhere, all the time, splitting the whole of reality again. It is a tree branching into more limbs than there are atoms in the observable universe, and on almost every limb there is a version of you, and not one of them can ever see the others. There is no randomness in this picture, because nothing is discarded. Everything that can happen does happen somewhere on the tree. The price is the tree itself, an endlessly multiplying forest of unreachable worlds, and the strange comfort that every choice you did not make was made by a you that you will never meet. The third physicist has been waiting, because he thinks both of the others gave up too early. This is the pilot wave picture, sketched by Louis de Broglie back in the 1920s, and revived fully and carefully by David Bohm in 1952. To this physicist, the particle is never in two places, never smeared, never a ghost. It has a definite position at every instant, the way a stone has a definite position. What it lacks is a definite path you can see, because riding alongside the particle is a real physical wave, spreading through every slit and every route at once, and that wave steers the particle like a current steers a boat. Think of a cork bobbing on a hidden wave. The cork is solid and single and always somewhere exact. But the swells that push it move through the whole pond, through openings the cork itself never touches, and so the cork ends up in places that only make sense once you account for water you cannot see. That is the pilot wave particle. Its fate was fixed from the start, guided invisibly, fully deterministic, no dice anywhere. This buys back the certainty that Copenhagen threw away. It costs something you may find just as strange. The guiding wave is non-local. A nudge in one corner of the setup can steer the particle instantly, no matter how far away the rest of the wave reaches, an influence that looks from the outside faster than light. The fourth physicist thinks all three of the others are dodging the real job. The others just interpret the same math. This one wants to change the math. This is the objective collapse camp, and its clearest form is the model built by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber in 1986, usually just called GRW, later smoothed into a version known as continuous spontaneous localization. Their idea is bold in a way the others are not. The collapse is real and physical, and it happens on its own, with no observer required at all. Every particle, left alone, carries a tiny chance per moment of spontaneously snapping to one sharp location. For a single particle, that chance is so faint it might not fire for hundreds of millions of years. But objects are not single particles. Objects are enormous crowds of them, bound together, and in these models the collapse of any one member drags the whole crowd along. So the rate scales with size. A lone atom stays quantum almost forever. A cat made of uncountable particles all locked together collapses to alive or dead in a sliver of a second, entirely by itself before anyone opens any lid, This is why you never catch a large thing mid-blur. Not because you looked, because it self-destructs into one state spontaneously, and the bigness of the object is exactly what pulls the trigger. Roger Penrose and Laios Diossi pushed a related idea from a different direction. They suspect gravity is the trigger. When a heavy object sits in a superposition of two places, each place carries its own gravitational field, and once those two fields differ by enough, the strain forces a collapse. That would make the collapse a hidden seam where quantum mechanics and gravity finally touch. Now sit with what these four physicists have actually done. One says reality is random and refuses to explain the randomness. One says reality never chooses and branches forever instead. One says reality was decided all along and only pretends to gamble. One says reality quietly destroys its own blur on a schedule set by mass. 4 pictures, one random, one infinitely branching, one secretly fixed, one spontaneously snapping. And here is the thing that has kept this argument alive for a century. For every experiment ever performed, they all predict the same result. Fire the particles, run the counters, read the screens. The numbers come out identical no matter which physicist is right. The fight was never about the data. The data does not care. The fight is about what is real underneath the data, and the shared math hides the answer with perfect discipline. That is why, if you poll working physicists, you find no winner. Informal counts at conferences, taken again and again over the decades, keep coming back split. Copenhagen-style views, many worlds, pilot wave and its cousins, each pulls a real and roughly comparable share, and a huge number of physicists refuse to vote at all. They use the math, they get the right answer, they build the laser and the chip and the sensor, and they decline to say what it means. Shut up and calculate, the saying goes. It is not laziness, it is a truce. When 4 pictures agree on every prediction, choosing between them can feel less like physics and more like taste. But there is one crack in that truce, and it is worth staying awake for. Remember that only the 4th physicist changed the math. The objective collapse models add new physics, and new physics has a fingerprint. If the wave function really does snap on its own, and if that snap jostles a charged particle, then the particle should shed a faint flash of radiation as it lurches into place, a whisper of X-rays thrown off by the collapse itself through a process called Bremsstrahlung. Standard quantum mechanics predicts no such glow. The collapse models cannot avoid it. So for the first time, the interpretations disagree not about meaning, but about a signal you could actually go and hunt. So physicists went hunting. In 2020, a team took ultra-sensitive germanium detectors deep into the Gran Sasso laboratory in Italy, buried under nearly a mile of rock to hush the constant sleet of cosmic rays. There they listened for that predicted whisper of X-rays, the faint proof that reality snaps itself into place on its own. They listened, and they heard nothing. Nothing at the level the models required. That silence ruled out the simplest version of the Diossi-Penrose gravity collapse idea outright, and it squeezed the continuous spontaneous localization models hard. The original 1986 GRW proposal did not quite die. It survived, but only just by a whisker, backed into the last thin corner of parameter space it had left. A follow-up in 2022 tightened the noose further, using the Majorana demonstrator experiment nearly 5,000 feet underground in South Dakota, listening again and again hearing that same telling quiet. Notice how rare and how precious that moment was. For once, an interpretation of quantum mechanics stuck its neck out and made a prediction the others did not share, and the universe answered. Not with a proof of what is real, but with an elimination, one option pushed to the edge of the map. And notice too how little it settled. Ruling out the simplest collapse model does not crown many worlds. It does not vindicate the pilot wave. Copenhagen and Everett still make identical predictions by design, and no germanium detector on Earth will ever tell them apart. The most that any experiment has managed is to trim one branch off the argument while leaving the trunk standing. So the war goes on, patient and unresolved, exactly where a century of the sharpest minds alive have left it. You can hold the cork bobbing on its hidden wave in one hand, fully certain and secretly steered. You can hold the tree branching into more limbs than there are atoms in the observable universe in the other, nothing lost and nothing chosen. You can keep the old shrug of Copenhagen, or wait on the last whisker of a collapse the detectors are still trying to silence. All of them fit the same numbers. None of them can be shown today to be the true face of the world. The box stays sealed in a deeper way than you first thought. Not just closed, but undecided about what closing even means. So some physicists decided the argument had gone on long enough, and they tried to force the question closed. Not with a bigger telescope or a colder chamber, but with pure logic, sharpened to a point. The tool they reached for was the oldest puzzle in the room. Take Wigner's friend, that sealed lab where one observer measures a definite result, while a second observer, standing outside, still describes the whole lab as an unresolved blur. For decades it sat as a curiosity. Then people started asking what happens if you nest those observers inside each other and let them all reason with correct quantum mechanics at the same time. The physicist Čáslav Bruckner turned that question into a formal no-go theorem, and in 2018 two researchers named Daniela Frauschiger and Renata Renner published a result that landed harder still. They built a thought experiment with several observers, each measuring, each reasoning flawlessly, each trusting what the others concluded. And they proved that the observers end up contradicting one another. One participant becomes certain an event happened. Another becomes equally certain it did not. Both used the same equations. Both were right by the math. Think about what that means for a moment. Not that someone made an error. That two careful observers can validly disagree about whether something in the world actually occurred. The theorem does not tell you who is correct. It tells you that no single, shared story of the facts can survive if you insist that quantum mechanics applies to observers themselves. The work was considered important enough that Bruckner's theorem and the Frauschiger-Renner result jointly earned the 2023 Paul Ehrenfest Best Paper Award for Quantum Foundations, nearly 60 years after Wigner first sketched his friend on paper. The puzzle did not shrink under scrutiny. It grew teeth. If you find any of this strange, and you should, a quiet like or subscribe helps more people find these long walks through physics. We are on Spotify too if you prefer to listen in the dark, but logic alone cannot settle what reality is doing, because every interpretation is built to survive it. So a different group of physicists went looking for a crack you could actually measure. They went underground. The objective collapse models, the GRW proposal from 1986, and its refinement called continuous spontaneous localization, are unusual because they add new physics, and new physics leaves fingerprints. These models say the wave function collapses on its own, spontaneously, at a tiny rate for a single particle and a furious rate for anything large. And here is the testable part. When a charged particle gets jolted by one of those spontaneous collapse events, it should radiate. It should emit a faint spray of X-rays through a process called Bremsstrahlung. The lighter charged particle gives off when its motion is suddenly disturbed. Collapse, if it is real and physical, should glow, just barely. So the search became a search for that glow. In 2020, physicists brought ultra-sensitive germanium detectors down into the Gran Sasso underground laboratory in Italy, buried beneath a mountain to shield them from the constant rain of cosmic rays that would drown out any faint signal. They watched. They counted every stray X-ray, and at the level the models predicted, they found nothing. That silence was itself a result. It ruled out the simplest version of the Diosy-Penrose model, the idea that gravity itself pulls superpositions apart. It squeezed continuous spontaneous localization into a much tighter corner. The original 1986 GRW model survived, but only just, hanging on by a whisker, its allowed parameters shaved down to a narrow strip. The picture here is worth sitting with. An ear pressed to a mile of rock, listening for a click that never comes. Each null result does not prove collapse is fictional. It only says that if collapse is real, it must be quieter, rarer, gentler than the theory first guessed. The theory retreats. It does not die. It just gets harder to believe in its bolder forms. Then, in August 2022, the hunt went deeper still. A second experiment took up the search, this one called the Majorana demonstrator, running nearly 5,000 feet underground at the Sanford Underground Research Facility in South Dakota, in the tunnels of a former gold mine. It was built to look for other rare events, but its exquisitely shielded germanium was perfect for this too. It looked for the same spontaneous X-rays, with even better sensitivity in key ranges. And it tightened the constraints further. Another stretch of silence, another narrowing of the possible. The window in which collapse could hide grew thinner by another notch. Somewhere out there is a version of these models so faint it may never be caught. And somewhere out there is the possibility that there is nothing to catch, because collapse never happens at all, and the superposition simply never ends. The underground detectors cannot tell you which, they can only keep listening. While the tunnels stayed quiet, the argument spilled out into public in a way it rarely does. In December 2024, Google unveiled its Willow quantum chip, and in its own framing of the achievement, the company suggested that the computation was so vast, so far beyond any ordinary machine, that it must be borrowing from parallel realities to find its answer. That word, must, did a lot of work. It reached straight for the many worlds picture, the idea that every branch of the wave function is a real universe, and planted a flag there in a press release. The pushback from physicists was quick and pointed. Many argued the claim overstated the evidence, that a fast quantum computation demonstrates the power of superposition and interference, but does not prove that other worlds exist, because every interpretation predicts that same computation. Many worlds says it, Copenhagen says it, Pilot Wave says it. The chip cannot referee between them, because they all agree on what the chip will output. To say the machine proves parallel realities is to smuggle a philosophy in through an engineering result. That was the objection, and it was a fair one. What that whole flare of argument revealed is how little the ground has shifted underneath the smartest people in the field. When you actually poll working physicists, and people have done this at conferences for decades, no single interpretation commands a majority. Copenhagen-style views, many worlds, Pilot Wave, and the rest, each draw a substantial, roughly comparable following, and the most popular stance of all, in daily practice, is to refuse to choose. Shut up and calculate, the phrase goes. Use the mathematics which never fails, and decline to say what it means. A century of the finest minds available, and the honest tally is that the vote is still split, the case still open, the meaning still undecided. So notice where all this effort has led. Logicians sharpened the paradox until two honest observers could disagree about whether an event even happened, and the paradox held. Experimentalists buried detectors under a mountain and under a mile of rock, and listened for the faint click of collapse, and heard only silence that narrowed the theories without killing them. And when a company tried to declare victory for one picture of reality, the field simply declined to accept it. Every attempt to force the question closed has left it open, only more precisely open than before. The boundaries have moved, the mystery has not. And while the interpreters argue over what is real, the experimentalists have been quietly doing something stranger, making the superpositions bigger. And while the interpreters argue over what is real, the experimentalists have been quietly doing something stranger, making the superpositions bigger. Not richer in theory, bigger in the plainest sense, heavier, wider, made of more atoms. The question they are chasing is simple to say and brutal to answer. How large can an object be and still interfere with itself? Back in 1974, that record belonged to a single electron. one lonely speck of charge passing through two slits and landing where a wave says it should. That was the frontier then, a single particle, barely there at all. And ever since, the record has crept outward, year by year, from that one electron toward things you could almost imagine holding. You do not need to memorize the numbers tonight. Let them pass over you like weather. But if a like or a subscribe finds your hand on the way, it helps this quiet channel drift into someone else's night. We're on Spotify too for the same slow hours. Consider where the record stood in 2019. A team at the University of Vienna, led by Marcus Arndt, built a machine 2 meters long, a matter wave interferometer purpose-made to catch large things behaving like waves. Into it they sent molecules, not simple ones, hot sprawling organic molecules, each a tangle of hundreds of atoms clinging together. One of them carried a formula you would never speak aloud in ordinary life. C707A260F92 ZN4. Read it slowly and it is almost a spell. 707 carbon atoms, 908 fluorine atoms, nearly 2,000 atoms in a single molecule, a mass over 25,000 atomic mass units, and that whole tangled object, fired down the 2-meter machine, arrived on the far side laid out in the soft stripes of interference. Think about what that means. A molecule of nearly 2,000 atoms did not choose one path. It spread. It went as a wave. It passed, in some real sense, through more than one route at once, and then folded back into a pattern only a wave could make. Something you would picture as a hard little clump of matter behaved like a ripple. That was the record, for a while. Then, in January 2026, the same Vienna group broke it again. Sebastian Pedolino led the paper. Stefan Gerlich was there, and Klaus Hornberger held up the theory behind it, and it landed in the journal Nature. This time the object was not a molecule at all. It was a nanoparticle, a cluster of sodium atoms between 5,000 and 10,000 of them, packed into a single grain about 8 nanometers across. Its mass was near 170,000 atomic mass units, roughly the weight of small protein. And they sent it through an interferometer they call muscle, and it delocalized. It smeared itself across a stretch of empty space dozens of times wider than the particle itself. Picture a grain of sand deciding to be a small cloud, and holding that indecision for a measurable moment. That moment lasted about 1/100th of a second, which sounds like nothing. But for an object of that size, 1/100th of a second of open superposition is astonishing. The team reported a macroscopicity, a formal measure of how deep into the everyday world the effect reaches, about 10 times beyond anything achieved before, one clean order of magnitude past every earlier record. So a grain far too small to see, smaller than a virus, held motionless by nothing but the pressure of light, in a vacuum emptier than most of outer space, was coaxed to blur across space many times its own width. Then measured, to prove it truly did. A whisper smeared across an empty room and then caught in the act. But mass in atomic units is one way to feel scale. There is another that lands harder. And for that we go back a little, to May of 2023, and a laboratory at ETH Zurich. There a group including Matteo Fidel and Marius Bill did something that sounds impossible when you first hear it. They took a crystal you could see, a chip of sapphire, gem grade, weighing 16 micrograms. Small, yes, but visible to the naked eye. A thing you could set on your fingertip. Inside that crystal sat roughly 10 to the 17th atoms, 100 quadrillion of them, several billion times the mass of any single molecule ever put into superposition before, and they made it vibrate 2 opposite directions at once, not one direction then the other, both. The entire chip of sapphire, its 100 quadrillion atoms, humming in a superposition of 2 opposing motions in the same instant. To read that fragile state, they wired the crystal to a superconducting qubit, a tiny circuit that could feel the crystal's condition and carry the answer out. A gem held between 2 fingertips, silently moving 2 ways, and a small electronic ear listening to confirm it. Now hold on to one detail because it keeps the wonder honest. The physical distance between those 2 opposite motions was tiny, about 2/1000th of a nanometer, far smaller than the crystal, far smaller than a single atom inside it. The separation was microscopic, but the object doing the separating was not. It was a thing your eye could find on a lab bench. That is the strange bargain at this frontier. You can make the object bigger, or you can make the separation bigger, but pushing both at once is the war. The sapphire crystal is enormous, and its split is vanishingly small. The Vienna nanoparticle is far lighter, but it spreads across dozens of times its own body. Each record trades one kind of largeness for another, and each one edges the whole enterprise closer to your scale. There is a third axis too. Not size, not spread, but time. How long can you keep the blur alive before the world erases it? At the University of Science and Technology of China, researchers built a cat-state superposition out of about 10,000 ytterbium atoms, a blended state of the kind Schrödinger meant to mock. 10,000 atoms all held in the same delicate 2 things at once, and it survived. Not for a millisecond, not for a fraction of a second. It lasted 23 minutes and 20 seconds. Sit with that. Most superpositions die in less than a heartbeat, killed by the smallest touch of the surrounding world. This one held its breath for over 20 minutes, long enough to walk across a room, pour a drink, and come back to find it's still undecided. And the machines that make all of this possible sit in a strange kind of silence. Levitated nanoparticles trapped by laser light, laser-cooled, floating in near-perfect vacuum. Groups at ETH Zurich, at ICFO in Barcelona, at the Austrian Academy of Sciences hold these grains suspended on nothing and coax them toward quantum stillness. They are not doing this only to break records. They are building platforms aimed at a deeper question. They want to test whether gravity itself collapses superpositions. The idea from Roger Penrose and Laios Diossi is that when an object sits in 2 places at once, the 2 versions of its gravity disagree and pass some threshold that disagreement forces reality to choose. A levitated mass split and held might one day feel that pull. 2 separate floating grains entangled with each other might one day show whether gravity is the thing that ends the blur. That experiment does not exist yet, but the tools inch toward it. And then there is the other giant in this room, the quantum computer. Because a computer built on qubits is, underneath, a machine for holding thousands of superpositions in careful formation at once. In December of 2024, Google announced a chip called Willow, 105 qubits. It ran a benchmark task called random circuit sampling, and it finished that task in under 5 minutes. Google stated that the same computation on a classical supercomputer would take about 10 to the 25th years, 10 septillion years. That figure is almost impossible to hold in your mind honestly, so let it settle slowly. 10 septillion years is roughly 700 trillion times the current age of the universe. Not 700 times. Not 700 million times. 700 trillion times the entire span since the Big Bang. And the chip did the equivalent work in under 5 minutes, humming quietly inside its refrigerator on a bench. Here you should be careful, and the physicists are careful. Google framed part of this by suggesting the computation was so vast it must be drawing on parallel realities, a nod toward the many worlds picture. Many physicists pushed back. That framing is a story told about the result. It is not a proof of any interpretation. The chip does not prove worlds are splitting. It proves that superposition, kept alive and marshalled, can do arithmetic no ordinary machine can touch. The interpretation is decoration. The performance is real. And keeping that performance alive demands cold beyond ordinary cold. These processors run near 10 to 20 millikelvin, about 100 times colder than the empty space between the stars, which averages around 2.7 Kelvin. They are chilled by dilution refrigerators that mix helium-3 and helium-4. shaped like golden chandeliers of descending stages, each colder than the one above, threading thin wires down to a chip at the bottom. All of that machinery, all that engineered silence exists to protect a blur from the touch of the world. So look at the ladder these experiments have built, a single electron in 1974, a molecule of nearly 2,000 atoms in 209, a visible sapphire crystal of 100 quadrillion atoms in 2023, a nanoparticle cluster spread across dozens of times its own width in 2026, a cat state of 10,000 atoms held for over 20 minutes, and a 105-qubit chip outrunning the age of the universe. Each rung is a different kind of bigness, and each one was declared impossible not so long before it happened. None of these objects is a cat. None of them is a person. The gap between a sapphire chip and a living thing is still immense, and decoherence still guards that gap ferociously. But the line that was supposed to separate the quantum from the everyday keeps moving. It moves every time a team builds a colder chamber, a longer machine, still a trap. And nobody has found where it stops. There may be no natural edge at all, only the practical difficulty of holding the world at bay a little longer. That is the quiet astonishment of this frontier. Every year, someone takes a thing slightly closer to something you could hold and puts it into two states at once and measures it and shows it worked. The gem on the fingertip silently moving two ways, the whisper smeared across the empty room, raw narration follows. Insert B, named objects, missions with numbers, written to flow into the anchor sentence. It helps to stop talking about particles for a moment and start talking about objects. Real ones. Machines with serial numbers, sitting on benches, in a handful of buildings scattered across the world. Because superposition is no longer a thing that happens only to electrons you cannot see. It happens now to things you could hold. Start in Zurich. Inside a laboratory at ETH Zurich, physicists took a small slab of sapphire and made it move in two directions at once. The crystal weighs about 16 micrograms. By any kitchen scale, that is nothing. But packed inside that speck sit roughly 10 to the 17th atoms, 100 quadrillion of them, locked into a lattice. That makes the crystal several billion times heavier than a single molecule. And here is the part that should sit oddly with you. It is visible. You could set it on your fingertip and watch it catch the light. They did not simply cool it and hope. They wired it to a superconducting qubit, a tiny circuit that lives fully in the quantum world, and they used that circuit to hand the crystal its strange instruction. Vibrate one way, vibrate the other way, do both. The whole slab of atoms was coaxed into a superposition of two opposite oscillations at the same time, pushing out while pulling in, leaning left while leaning right. You want to know how far apart those two motions actually were. The answer is almost nothing. The separation between the two vibrational states measured only about 2 billionths of a nanometer. A distance so small it makes an atom look like a mountain, and yet the object doing it was large enough to see. That is the tension the whole field lives inside. The weirdness is microscopic. The thing carrying it is not. Now travel to Vienna. There, a group has spent years building machines whose only purpose is to catch bigger and bigger things behaving like waves. Their newest one has a name. They call it Muscle. It is a matter wave interferometer, a long careful instrument that takes an object, splits the path it might take, and then checks whether the object interfered with itself along the way. In January of 2026, that group fed it something remarkable. Nanoparticles built from clusters of sodium. Each cluster held somewhere between 5,000 and 10,000 atoms. In the language physicists use for mass, that comes to about 170,000 atomic mass units, roughly the weight of a small protein, compressed into a grain about 8 nanometers across. They sent these grains through muscle, and the grains delocalized. Each one spread across a region dozens of times its own width, existing as a smear of possibility rather than a dot, and then landed in the banded pattern that only a wave can make. They keep a number for how impressive this is. They call it macroscopicity, a single figure that rates how far an experiment pushes quantum behavior toward everyday scale. The sodium clusters scored about an order of magnitude beyond anything done before. 10 times deeper into the forbidden territory, the region where you and your morning coffee are supposed to live and quantum blur is supposed to be impossible. Then there is a record that had nothing to do with size and everything to do with time. Travel east to the University of Science and Technology of China. There, researchers built a cat state. That is the lab word for a superposition of a large collection of particles all committed to two opposite conditions at once. The direct descendant of the imaginary cat in the sealed box. Theirs used about 10,000 ytterbium atoms. Most superpositions are gone almost before you can name them. They last fractions of a second. A millisecond is often a triumph. The atoms in this experiment held their superposition unbroken for 23 minutes and 20 seconds. Read that again slowly, not a millisecond, not a second. More than a third of an hour, a bundle of 10,000 atoms sitting in two contradictory states, refusing to decide, while the clock on the wall ticked through more than 1,000 ordinary seconds. To do any of this, you need cold. Not winter cold, not the cold of dry ice or liquid nitrogen. You need a cold that the natural universe never quite reaches on its own. And that means the last object in this gallery is the machine that makes the cold. The dilution refrigerator. It deserves your attention because it is doing something no ordinary freezer can. It runs on a mixture of two rare forms of helium. Helium-3, the lighter one, and helium-4, the heavier one. When you chill that mixture far enough, it does something almost unbelievable. It separates into two layers, like oil resting on water, and then atoms of helium-3 are pulled across the boundary from the rich layer into the thin one. That crossing costs energy, and the energy it steals comes out as heat drawn from everything nearby. The mixture, in effect, sweats cold, and it can keep sweating for as long as you keep the cycle running. The temperature it reaches is the reason these experiments exist at all. A good dilution refrigerator brings its coldest stage down to somewhere between 10 and 20 millikelvin. That is hundredths of a degree above absolute zero, the floor below which nothing can go. To feel how strange that is, look up. The empty space between the stars is not truly empty of warmth. It hums with the faint afterglow of the Big Bang, and that glow keeps the void at about 2.7 Kelvin. The chip inside one of these machines is held roughly 100 times colder than the darkness between the stars. You would have to leave the galaxy and keep going, and find the emptiest gap in the universe, and you still would not find anything this cold occurring on its own. It exists only where people build it on purpose. Picture the machine itself because the shape matters. A dilution refrigerator does not look like a box. It hangs. It is a series of round metal plates, stacked one below the other, each one wider work than a dinner platter, each held apart by slender posts. The plates are often plated in gold, both to reflect stray heat and to conduct it away. Each plate is a stage, and each stage is colder than the one above it. The top is merely frigid, the next is colder, the next colder still, and at the very bottom, dangling from the coldest plate of all, sits the chip, the qubit, the crystal, the atoms, the thing you actually care about, suspended at the deepest point of the cold. Threading down through all of it are the wires, hundreds of them, thinner than a hair, running from the warm world at the top to the frozen chip at the bottom. They have to be thin on purpose. A thick wire would carry heat straight down and ruin everything, like leaving a door open in winter. So the wires are drawn out fine and delicate, just enough metal to carry a signal and almost none to carry warmth. When you see one of these machines in operation, gold and tiered and glinting under the lab lights, the image that settles over you is unmistakable. It looks like a gold-plated chandelier sinking stage by stage into deeper cold, each level a little further from the ordinary world, until the last faint tier holds a single point of matter colder than the space between stars. That chandelier is not decoration. It is the whole reason the crystal in Zurich could vibrate two ways. the reason the sodium clusters in Vienna could smear into a wave, the reason 10,000 ytterbium atoms in China could hold their impossible pose for more than 20 minutes. Warmth is noise. Warmth is the constant jostle of the everyday world reaching in and forcing the question, which one is it? Until the superposition gives up and answers. Take the warmth away, take nearly all of it, and the question stops being asked. The blur is allowed to last. So lay these objects side by side the way you might lay coins on a table. A speck of sapphire you can see, moving two ways at once. A grain of sodium 8 nanometers wide spread across a space dozens of times its size. 10,000 atoms holding two truths for 23 minutes and 20 seconds, and beneath each of them, cold golden tears of a machine reaching for a temperature the universe never volunteers. Every one of these is heavier or slower or more stubborn, or simply more visible than the experiment that came before it. Everyone drags the strangeness a little further out of the atom and a little closer to the room you're lying in. Each record falls a little closer to your own scale, and the wall between the quantum world and yours starts to look less like a wall and more like a question no one has answered. Word count, approximately 1,590 words. Pre-flight 1 line each. Word budget 1,600, within 10%. Pass, go to the 90. Opens as natural continuation. No header, preamble. Pass, ends. So anchor reads naturally after it. Pass, anchor is the final paragraph. Named objects with numbers. 16 micrograms, 1017 atoms, 2 billionths nm, 170,000 AMU, 8 named 10,000 atoms, 23 min 20 sec, test 20 mk, 2.7 k. Pass, no dashes as punctuation anywhere. Pass, ASCII only, no markdown, timestamps in narration. Pass, tactile metaphor, gold-plated chandelier sinking stage by stage into deeper cold. Pass, no canonical scaffold phrases used. Pass, second person, calm register, short sentences. Pass, units imperial, allowed exceptions. Kelvin, nanometer scale. Pass. Note, no local. Write tool is available in this session, so I could not persist to press just Claude. Agents, just DSD scripts. The finished insert is delivered in line above as raw narration. If you want it saved, tell me the destination. A local path needs an interactive session with file system access, or I can upload it to Google Drive. Each record falls a little closer to your own scale, and the wall between the quantum world and yours starts to look less like a wall, and more like a question no one has answered. Each record falls a little closer to your own scale, and the wall between the quantum world and yours starts to look less like a wall, and more like a question no one has answered. So let the thread gather quietly now. Pull it back through everything you have followed tonight and see where it leads. It leads to an open case, not a solved one. A century of the sharpest minds who ever lived have stood exactly where you are standing, at the edge of this question, and none of them closed it. Niels Bohr said the wave function was only our knowledge, and that measurement caused a real and random collapse he never explained. Hugh Everett, in his 1957 Princeton thesis, said nothing collapses at all, that the universe simply keeps branching, a new world for every possible outcome. David Bohm said the particle always had a definite path, guided by a hidden wave. Others said gravity itself reaches in and snaps the blur into place. 4 pictures, one random, one endlessly splitting, one secretly fixed, one quietly self-destructing. And every one of them predicts the exact same result, every single time. That is the strange heart of it. The disagreement is not about the data. The numbers match, the Born rule holds, the experiments repeat, clean and reliable, in labs cooled to 20,000ths of a degree above absolute zero, colder than the empty space between the stars. The machines work, the predictions land, and still, no one can tell you what is actually happening underneath. So let the idea settle, softly, without needing to win. Reality, at its smaller scale, genuinely seems to run on possibility rather than fact. A particle fired alone, with nothing else in the universe to touch, still behaves as though it tried both paths at once. A crystal you could hold between two fingers has been made to vibrate two opposite ways in the same instant. A cluster of thousands of atoms has been spread across a stretch of empty space dozens of times its own width, and then measured and found to have been in more than one place while no one looked. And then something looks. Not a person necessarily, just the world. A single stray photon, a passing air molecule, one irreversible touch, and the blur commits. It picks. The many become one. Physicists call the leak decoherence, and they can time it now, down to the millisecond. Watch it erase the strangeness faster than any instrument or any mind could ever catch. But timing it is not the same as understanding it. Nobody agrees whether the looking causes the answer, reveals an answer that was always there, or splits the world so that every answer quietly comes true somewhere else. Richard Feynman, who understood as much of this as any human ever has, told a room full of people in 1964 that nobody understands quantum mechanics. 60 years on, that sentence has not aged a day. Now turn it gently, from the far edge of the lab back toward yourself. Because you are not outside this. You are made of the very same particles that behave this way, the same electrons that pass through both slits, the same possibility that refuses at the bottom to be just one thing. And the only reason you feel solid, single, certain of exactly where you are, is that you are held to one answer by an unbroken storm of touches, trillions of collisions every instant, air against skin, light against surface, warmth spilling outward, each one a tiny measurement, each one erasing any blur you might have carried before you could ever notice it. You're not sharply defined because reality decided you should be. You're sharply defined because the world will not stop looking at you, not for a single nanosecond, and that endless looking is the only thing pinning you to one place. There is something oddly gentle in that. You spend your days feeling like a fixed and separate thing, moving through a settled world. And underneath, the truth is softer and stranger. You are a possibility held to one shape by the constant, patient attention of everything around you. The certainty you live inside is not carved in stone. It is woven, moment by moment, out of countless small entanglements you will never see. And it is remade for you every instant you are alive. So you can lay the question down now, still open, and rest right beside it. You do not have to solve the deepest unsolved problem in physics before you sleep. The smartest people alive have not, and the world turns anyway. The crystal still vibrates two ways at once until it does not. The cluster still spreads and commits. The case stays open, and somehow that is a kind comfort rather than a cold one, because it means the ground you stand on is quietly, endlessly generous, choosing one gentle answer for you over and over without being asked. Let that thought loosen in your chest like a held breath finally let go. There is nothing left to hold. The particles will keep being particles whether you watch them or not. The interference bands will keep forming dot by patient dot on screens in quiet rooms while you dream, and the world will keep doing for you what it has always done, holding you to one soft and single answer, so that you can close your eyes and simply be here, whole and warm and undecided about nothing that matters right now. The question can wait. It has waited 100 years. It will keep gently until morning. Sleep well tonight. Good night.